Hi, this is flip class video 2 for Chemical Engineering Thermodynamics 2. And the topics for this video would be the chapter 11.4 in the textbook. And it covers the mixture of ideal gas. And ideal gas mixture would be, say, how many species combined, but all species remains under assumption of ideal gas. So if we want to find the partial molar volume of one species in the mixture, this is a definition of partial molar volume, right? And it is partial differentiation of total volume of the mixture with respect to number of moles of species of our interest when temperature, pressure, and number of moles of other species remains constant. In this case, if we applied ideal gas law, and total volume of gas can be represented by ideal gas law if all gases in the mixture behave according to ideal gas, right? So a total volume can be represented by nRT over P. And in this case, R is constant. This is gas constant. It is constant for sure. Temperature and pressure in this particular equation, they are constant because we put it there. The differentiation are considered only when temperature and pressure are constant. So therefore, we can take all three variables here outside differentiation. So what we have would be something like this. And then if we consider N in this case is a total number of moles of our species combined, where Ni is number of moles of one species I of our interest only. So if we expand N here to be the combination or summation of all number of moles, let's say if we have M species, we will have M term here. So if you take differentiation of this N with respect to Ni here, you should have differentiation of N1 with respect to Ni, differentiation of N2 with respect to Ni. And in this case, since we already put that Nj, or number of moles of all other species rather than species I, are constant, differentiation of N1 with respect to Ni would equal to 0. So does the N2 until Nm. The only term that is not 0 would be Ni itself. If you differentiate Ni with respect to Ni, you'll get 1. So this term, differentiation term, would ultimately become 1. And therefore, you can get partial molar volume of species I in the mixture equal to RT over P. And remember that T and P are temperature and pressure of the mixture. All right, so we can represent partial molar volume of species I with simple equation like this, as long as our mixture behave like ideal gas. Now, we disregard the mixture for the moment, just forget about mixture, and try to find molar volume of pure species I, and in this case, species I behave like ideal gas. Then, since our species is pure at the moment, the volume can be written as Vi. This is pure species I. That can be represented by ideal gas law as well, right? This is molar volume. According to ideal gas law, it would be RT over P. So you can see that right now these two equations are essentially the same in the sense that properties of volume, molar volume of species I as pure species is equal to a partial molar volume or species I when it exists in a mixture. All right. Furthermore, if you calculate molar volume of gas mixture, that means we have mixture, now more than one species combined, you get total volume of the gas, and then divided by total number of moles, like so. This is molar volume of gas mixture. There's no subscript here. That means the whole variable represents mixture. It is obtained based on the total volume of the mixture divided by total number of mole in the mixture. All right. The denominator, total volume of the mixture, as long as the mixture is ideal gas, you can use ideal gas law. That would equal to RT over P. nRT over P, and N over here and N over there are essentially the same, so they cancel out, and eventually you get RT over P again. All right. So all three here give you the special circumstance that for this mixture, for this ideal gas mixture, you can get partial molar volume of species I. This one is for species I when it is inside the mixture. It should be equal to partial molar volume of gas in pure state. So this second one here represents molar volume when it is pure. And this one would equal to molar volume of the whole mixture. They are all the same because the mixture is ideal gas. And the first assumption of ideal gas is that all molecules in ideal gas does not have any interaction. Remember our first example in the first video, ethanol and water, the volume is changed because of interaction between molecules. So in this case, there is no interaction, so therefore summation of volume will be the same. There's no interaction, so therefore there's no change in molar volume. All right. So in order to prevent any confusion, we are going to put the subscript Ig to represent that right now we are talking about ideal gas. So Ig here stands for ideal gas. All right. Now, the second term that we need to discuss is called partial pressure. And partial pressure here is not the same as partial molar pressure. Don't be confused. In the first video, we said that partial molar pressure does not exist. This one does not exist. This partial pressure is the special variables that we define to give you something special, and we will explain it in a minute. According to definition, partial pressure of species I is defined as pressure when the species I would exert if it alone occupying the volume of the mixture. I'm going to explain this one simply by giving you the picture. Let's say we have the volume of the container. Inside the container, we have three species, A, B, and C. The total pressure or the pressure of the container here is P, capital P. So if I imagine separation of all three species like so. So instead of mix them together, suppose we can separate them. And the molecules of species A are together in this region, molecule of B are together as well. If I take another empty container with the same volume as this container and take only species A into the container here, transfer them into the container, and therefore it is gas, so therefore it should expand. The expansion should decrease the pressure, right? So if you have expansion of gas here, if you count the number of molecules of species inside this container, you see that within the same volume, the container here has less number of molecules. So you should expect that the pressure, if I measure the pressure here, the pressure is supposed to be lower, all right? This particular pressure in this system is defined and called as partial pressure of species A. We use the small letter PA here to say this is partial pressure of A. All right, this is definition of partial pressure. It is pressure when the species is taken out and occupying the same volume. All right. Now, if the system here or my gas here behave like ideal gas, so I can calculate number of moles using ideal gas law. And right now on the right hand side, the pressure is equal to small pa or partial pressure of A multiplied by volume divided by RT. On the left hand side, I can calculate number of moles of A here in this picture based on the total number of mole multiplied by mole fraction In this case, in gas phase, from now on, we are going to use YA to represent mole fraction of A in gas. XA would be mole fraction of A in liquid phase. All right. So from definition of mole fraction, Na would equal to Ya times N, or total number of moles in the left-hand picture. These two are equal, right? So I'm sorry. The Na here, this is total number of mole within this volume if all gases behave like ideal gas. So therefore, we can calculate N by using ideal gas law PV over RT. So on the left-hand side, we get this equation. On the right, we have another equation. But remember, NAs are the same. So these two are essentially equal. So equal, VRT would cancel out. And what you have left would be EA, which is partial pressure of A on the right-hand side, would equal to YA times P, this equation. So this equation gives you the way to calculate partial pressure of the species of your interest based on its concentration and total pressure. If you calculate this partial pressure for all species and combine them up, you get the second equation here. Summation of partial pressure would equal to summation of the right-hand side here. And P, which is pressure of the whole system, would remain the same regardless of which species you are interested in. So in the summation here, you can take P out and leaving only summation of Y, which is equal to 1 if you sum them for all species. So this term becomes total pressure. According to this equation, physically, it means that if you make summation of partial pressure, you should get the total pressure of your mixture system. Right. Then, before we moving on, there's a theory that gives the correlation between partial properties and partial pressure. The theory is called Gibbs theorem. The theory basically says that partial molar properties, any partial molar properties other than volume of one single species in the ideal gas mixture is equal to that properties of pure gas or properties of that species when it exists as pure gas at the same temperature, but the pressure would equal to partial pressure. Seems confusing. It's a very long sentence. So in short, mathematically, it can be written like this. This is partial molar properties. These properties is properties of species I in the mixture. So we put bar here to represent partial molar properties. All right. It takes place as temperature T and pressure of the mixture. It can be calculated to be equal to Mi here, which is properties of species I when it is pure at same temperature, but the pressure is reduced from capital P to small pi. This is partial pressure, right? So the sentence here can be translated to mathematical equation like this. This is true for all properties except volume, because before this point, at this point, earlier we have defined that volume they are all equal, right? But for anything other than volume, like enthalpy, or Gibbs free energy, you can use this equation. Now, we have to apply theorem to partial molar enthalpy. Like so, we just change properties M to enthalpy. Okay? So we can calculate partial molar enthalpy of I in the mixture based on molar enthalpy of POI at different pressure. However, this one is very easy because right now we look at ideal gas. The ID here, this is ideal gas. And for ideal gas, enthalpy is a function of temperature only. Enthalpy of ideal gas is not function of pressure. So it doesn't matter whether you use this pressure or that pressure, enthalpy is supposed to be the same. In other words, if you consider the right-hand side of the equation, and I want to find this value, I can get the same value if I increase the pressure from this small pi to capital P. So these two are essentially the same, basically, because enthalpy of ideal gas is a function of temperature only. As long as I keep the temperature to be the same, I can change pressure to any value. All right. So on the far right, this is properties of pure speci. On the left, this is properties of speci when it exists as part of the mixture. So therefore, this equation gives you that speci, enthalpy of speci, when it exists in the mixture, is not changed at all. It would be the same as it is pure, as long as the mixture is ideal gas. So, take partial molar enthalpy, and then you use summability relation. You multiply by mole fraction and sum them up for all species. You get enthalpy of the mixture. This is molar enthalpy of the mixture, right? So this is mixture. This is the species inside the mixture. Then we use equation from the above. You can say that partial molar enthalpy would equal to molar enthalpy of pure species. And therefore, if you combine these two, you can say that you can calculate properties of the mixture, the whole mixture, if you know properties of each constituent species. This can be done because of this equation. Same thing can be applied for internal energy, because internal energy of ideal gas is function of temperature only. So we can use the same equation, just change H into U, and you get the same relationship. So I'm going to skip on the internal energy. The other one that we need to calculate would be partial molar entropy. So right now we have entropy. All right. This one is in the mixture. This one is in pure. It can be calculated as long as pressure is changed to partial pressure. This is Gibbs theorem. Now, but these two are not equal, because even for ideal gas, entropy is function of temperature and pressure. So if the pressure are not the same, entropy are not the same. So in order to find this one, we need to change the pressure from this value to another value here, right? Remember, these two are properties of pure species. We just want to get this one from that one, okay? In order to find that, remember, since these two terms represent properties of pure species, we can use the relationship derived in chapter 6 earlier for pure species. For pure species of gas, we are talking about ideal gas, so it is gas, one phase only, and it is pure species, so one component only. For one component, one phase species, degree of freedom is equal to 2. Therefore, you can represent any change in properties with respect to two variables. If I choose temperature and pressure as two variables, I can use what I derived together with Maxwell equation written in chapter 6 to get this equation. Okay. Again, this equation is a simple equation used to calculate delta S for the change of temperature and pressure of pure species. Now, we are going to apply this one to find this term, and later be used for partial molar entropy of the mixture. Right. So let's get back to this equation. Now, from this stage to that stage, temperature are the same. So the dt here can be cancelled. They are the same, so it doesn't matter here. This term will be dropped. From this state to that state, we change the pressure only. So in order to get this one, we simply just integrate the second term. All right. But the second term here, we need to put V to change To get a relationship between V, T, and P, we are going to use equation of state. In this case, ideal gas equation of state, because we are talking about ideal gas mixture. If we put ideal gas law here, EV equal to RT, or V equal to RT over P, right? Put in there, differentiated with respect to temperature, we get R over P dP. And then integrated from one state to another. In this case, from state of PI, small pi, to state of capital P. And the entropy will be changed from this value, that value as well. Integration is simple because R is constant. On the right-hand side, you get logarithm. On the left-hand side, you get the S, or difference between two states. Difference between entropy of two states. Right-hand side, you get logarithm. Okay? So if you rearrange this equation, and you realize that small pi here is called partial pressure. By definition, it is mole fraction multiplied by total pressure, capital P. And this capital P and that P are the same, so it can cancel out. What you get will be 1 over yi. Then rearrange this equation at this part. So from this, if you compare with the one above here, this left-hand side is what you are going to use according to Gibbs theorem. The right-hand side is the one that you are going to have. This is properties of pure species at the same temperature and the same pressure as the temperature and pressure of the mixture. All right. So if you plug this to here, then you can calculate partial molar entropy of your species in the mixture. Now, using summability relation, partial molar entropy combined, you get molar entropy of the mixture. And then partial molar entropy can be calculated according to Gibbs theorem, equal to this term, and this term can be calculated based on that equation. So plug this into this, plug that into that, you get this equation. All right. So it means that you can calculate properties, entropy of the mixture, if you know entropy of pure species, multiplied by concentration or mole fraction and added by this term. So it is convenient that you can calculate properties of mixture using properties of pure species. But you have to remember that all terms here are the term at the same temperature and pressure. But physically, they are different. Don't be confused. This one is the mixture properties. This one is properties of one single species in the mixture. The difference between these two is that the one on the left is the whole mixture. This one, the second one here, is for one species in the mixture. The one on the right is the same species, but in the status of the pure component. All right? The last one is partial molar Gibbs energy. We will start from fundamental relationship definition of Gibbs free energy. Gibbs free energy is defined as enthalpy subtracted by T times entropy. And you can use this equation for partial molar properties as well. H bar and S bar were already found. We calculate these two already, so we are going to plug it in. Earlier, we know that H bar of ideal gas mixture is equal to enthalpy of pure species, where S bar is equal to S of pure species added by one other term. Right? Just plug these two together to calculate free energy. We don't need to use theorem for this one because we got the relationship by definition already. Plug it in here. This is minus. This is minus. It turns to be plus, right? And then you can calculate partial molar Gibbs free energy as a function of everything on the right-hand side are properties of pure species. Then these two terms combined according to definition of Gibbs free energy, you get Gibbs free energy of pure species. So using summability relation, this is molar Gibbs free energy of the mixture, no subscript here, can be calculated based on partial molar Gibbs free energy, and then partial molar Gibbs free energy can be calculated based on this equation. Just plug it in there, and what you have would be these two terms combined. Once again, you can calculate properties of the mixture, of the whole mixture, based on properties of pure species that will be used to create that mixture. Now, this is fundamental relation that show relationship between G, V, P as T. If I write it down for pure species of ideal gas, everything would be properties of ideal gas pure species. I consider this equation at the state where the temperature is constant at temperature T1. If the temperature is constant, the second term here will be dropped. Okay, and then we have only these two terms left. Using ideal gas law, right now it is ideal gas mixture, so volume can be represented by ideal gas law, changing to RT over P. And then rearrange the equation, integrate the equation. On the left-hand side, you get G. On the right-hand side, RT is constant. Right now, remember, we taking the scenario for constant temperature. So temperature is constant. You have 1 over P dP. Integrated, you get logarithm of P. And since the integration has no limit, we need to put the integration constant C1. Now, C1 here, even though it seems to be constant, but it's supposed to be dependent on the temperature, right? T here would be T1 for this case. I write the same equation for another temperature T2. I'm going to get the same form of equation, but T here will becomes T2, and constant here would be another constant which is not the same as C1. Even though it is constant, it still depends on temperature, right? So these two are not the same. It's a function of temperature. So if I'm going to write down the equation like this for generic case, for any temperature, I can get something like this, giving that the constant here is a function of temperature. So I put temperature here in parentheses, just saying that this whole variable is a function of temperature. All right? Now, on the left-hand side of this equation, this is Gibbs free energy of pure species. This is pure species. So I'm to plug this back into equation above here. They are the same. So I'm going to get these two terms to be the same form. You have RT, you have logarithm, then you can combine. What you have together would be Yi times P, which is partial pressure. Okay? Now, this is summability relation. Properties of mixture equal to some summation of partial molar properties multiplied by mole fraction. If I write it down for free energy, I can get this equation. Notice that I change X to Y because right now our mixture is ideal gas. It's gas, it's not liquid. I put IT here just to say it's ideal gas. Okay? Then use this equation, plug it in here. After plugging this one back in there, rearrange the equation. Finally, I get this equation. So, in summary, for pure species I can write equation like this. This is for pure species. I can write the free energy of pure species like so. It depends on temperature, pressure. Note that this one will be constant at given temperature. For mixture, we consider species I in mixture. I can use this equation. You can write it down like this based on pure species give free energy. Or you can write it down using this one, plug it in here, you get another equation. So now this term will be partial pressure. If you write it down for all species and combine them, that means you sum them up. You get total or molar Gibbs free energy of total mixture as this equation. And then if you use Gibbs free energy of pure species, plug it in here, you can get this equation. This equation, these three equations will be important because we are going to use partial molar Gibbs free energy in the mixture later.